you can associate some quantity to this, and that will be bounded by some quantity. So basically this is a bound, and we will test every theory in this bound, and then we will check that only Einstein theory passed this test, and we will explain everything related to this process. Okay. So first I should mention that Somangshu, Shubham, Omio are collaborators, and Siraj is my guide in TIFR. Okay. So first I will explain a new rule to rule out many theories, and which will only allow Einstein. So that rule says that the S matrix or the scattering matrix of any consistent classical theory never grows faster than S square at fixed t. These small s and this capital S are not same. I will explain what this small s and small t is, and this happens at all physical values of momenta for every possible choice of the normalized polarization vector. So it might sound very complicated. I will explain it with some examples. Okay. So let's say you are considering a gravity actor, okay, and you have finite number of interaction terms. Okay, those kind of interaction terms we will say we will call them as truncated. Okay, so you don't have infinite number of interaction terms, and then each and every interaction term will grow at some power of s, right? So let's say the first term grows as s to the power 0, the second term grows as s, and then the third term grows as s square, and then the nth term grows as s to the power n, and then the series truncates there. Then at large s, definitely s to the power n will dominate, right? Considering large s and fixed t, remember this limit. Okay, so any scattering matrix have this behavior s to the power n. Now what this rule says, that basically this capital N can't be more than 2. That is, it is less than equal to 2 for all consistent classical theories. Okay. Now what do I mean by classical theories? I will just shortly explain it. The classical theory means if you are considering any QFT process, and that Feynman diagram can be written as an perturbative series, right? That is, the first term is no scattering diagram. The second term, in the second term, there is one scattering point. In the third diagram, two particle annihilates to a single particle, and then it decays to another two particle. Okay, so this kind of diagrams you will see, and there is an infinite series. Okay, now there is a fundamental difference between, you can categorize this all the diagrams in two categories. Okay, the first category will include these three diagrams, and then the second category will include everything else. What is the difference between these two theories is that here in the first case you don't see any loop in the diagram. Okay, here you will see in each diagram you will see loops. Okay, so these diagrams are called tree level diagrams. Okay, and usually classical results comes from only these diagrams. Okay, so if you want to get any classical result, you should take only those tree level diagrams, those diagrams without any loop. Then the result is now you can check this identity that n must be less than or equal to 2 for every interaction terms, and then you can see that only Einstein term passed this test. Okay, and it also saturates the bound. That is, for Einstein theory, this S behavior is exactly S square. Okay, and no theory have less than S square at classical level. There can be quantum corrections, but we are not considering that. Okay. So the rule is more or less, if it is clear, then we can go to some another possibilities. The another possibilities, if you don't have truncated series, right? Yeah, this is also can possible. And then one example you can think of, that 1 plus S square. These coefficients are not, I mean, it is just a schematic series, and then this series sum up to 1 by 1 minus S, right? then the largest behavior says that this falls off as 1 by s, and there is no growth, and that is slower than s square. So then it satisfies that new rule. So, but this is just an example, like it is a created example, but there is a concrete example for this non-truncated case, that is a string theory amplitude. The string theory amplitude is seen to grow as h to the power 2 plus some quantity, and this quantity is negative. Okay, it is always negative. Then you can see that this is a slower growth than s square. So there is a possibility that if your theory is not truncated, if you want to consider all possible interaction terms with a particular choice of coefficients or coupling constants, then you can have a good theory. Okay. So the plan of this talk is, first we will motivate that why in general two derivative theories, and especially Einstein theory, are generally good theories. Okay. So then we will motivate the proof of this new rule. Okay. Now let's start with some basic rules of quantum mechanics, how we got quantum mechanics, and that uses the phase space for and I have as you can see that I have got this results from Dirac's book, and I mean these are not results, these are basic things. Okay, so to get the quantum mechanics, what you do first you take a classical system and you identify generalized coordinates and the generalized momentum, right? And then you define a Poisson bracket between them, and this is this. Then you immediately define a quantum Poisson bracket from this classical one by this definition, right? So UV minus VU is just I cut times this. So you have just upgraded your variables from classical to quantum, and then the commutator becomes this Poisson bracket. Okay, so this is the definition, and from here you start doing quantum mechanics. Once you got this definition, you immediately define creation and annihilation operators, right? Then you define the ground state, where this annihilation operator will annihilate the state, and then you create the excited states by operating a dagger on this ground state. And then you got the whole Hilbert space, right? And that's a complete story, right? So yeah. So that's a good news. But the bad news is it is only valid for two derivative theories. We will say why this is only valid for two derivative theories. Let's say your Lagrangian is not dependent on only x and x dot, but it also depends on x double dot, right? So this x dot is related to pi, and x double dot is, let's say you have defined an fi, new coordinate, right? In the generalized, as a generalized coordinate. And then what, you don't know what is the Poisson bracket for this fi variable, and then you don't know what are the quantum commutators for this variable with x and p, and then your Hilbert space is not well defined for this case. So you see, in this simplest case, that you just introduced a new variable that is x double dot, and you don't know much about the quantum version of this classical theory. So what is the conclusion? The conclusion might be, it is our ignorance that we don't have a good higher derivative theory, quantization of this higher derivative theories, or maybe due to some physical reasons, higher derivative theories are not good, just not good. And you can predefine your logics, and then you can say these are not good. So we will mostly explore this second case, but we can't ignore this first case. I mean, we should have some equivalent of Dirac's quantization for these variables. Now we will find more evidence in QFT, so that this why two derivative theories are good theories. So let's first start with some basics. And so in field theory, we will consider only real scalar fields, and that is phi, and there is a conjugate moment of pi. These are the replacements of Q and P in the quantum mechanics. Okay, and that is defined by this from this Lagrangian, and we will consider this convention. Now for this field theory, one can write down an action, and the action looks like this. This is a free field action. Okay. This is the simplest action you can write for scalar field. And then in similar way, you define ground state, you define one particle excited state, that is psi1, that is you just act once with this phi operator. And then you define two particle excited state, that is phi square operating on 0, okay? And now there is a rule in this field theory, okay? So for any psi, the inner product of a same psi cannot be negative, okay? This goes in the name of unitarity, but what it says is that norm of any state can't be negative, okay? Now this is valid for every state. Then we will check for just the first excited state or the one particle excited state. For that also the psi1 must be greater than 0 and then 0. And then you see this psi1 is just one phi acting on 0, right? So then you can easily identify that psi1 inner product is just phi dagger phi acting on 0 and 0. You can ignore this dagger because we are dealing with real scalar fields, okay? And how to calculate this quantity? This is called, this has a name, and this is called 2-point function in the ground state. Right? So, and how to calculate this function? This is easy, and you can just substitute del any partial derivative with ik in the action and in this action, okay? And then you will get the 2-point function. And I have just calculated it, and there is some number by k square plus m square, okay? Then the rule 2, then from this 2-point function you can interpret some facts, and the facts are, this is called a particle propagator, and the propagator has a pole at k square is equal to minus m square, and that is the condition that any particle satisfies in special relativity, right? And then this pole has a residue, that the residue number is this is the number, and your rule 1 says this number must be greater than 0, okay? And it represents a particle in QFT, okay? These are the basic rules we will use in the next slide. Now we will consider some higher derivative theories with truncated interaction. Now we are considering this action. The first part you can identify, this is the free field part, and then there is some interaction, okay, with higher derivative term, right? Though it is a phi square term, so it's quadratic in phi. But anyway, this series truncates at this point, so there is no other term in this theory. For this action also, you can calculate the 2-point function, and the 2-point function is, you can just substitute del by ik, and then you can get this answer, right? 1 by k square plus m square was the previous answer, and then you got lambda k to the power 4, right? Now this 2-point function can be decomposed into 2 parts, right? Because it's a 4th order polynomial, it can be decomposed into this form, and then you see this number a and number b. These are undetermined still, but we will determine it soon. How to determine these numbers? You can just do a large K expansion of this left hand side and the right hand side, right? So left hand side says that at large K, this K to the power 4 is the leading term, right? So the series starts from K to the power 4. The next term will be 1 by K to the power 6 and so on, right? So there is no 1 by K squared term. That is very crucial. But in the right hand side, you see this number A plus number. So the leading term is number A plus number B by K square, right? So there is a 1 by K square term, and then the subleading terms are 1 by K to the power 4 and K to the power 6 and everything. But we don't need those terms. We just need to set this term to 0 because both sides should be equal. So then this number must be 0, right? So then you can immediately interpret that the number B and number A has a relative sign, right? So we don't know which one is positive, which one is negative, but we know that one of the particle will have negative norm state, right? So that breaks rule 2, right? What we started with. Now we have given some motivation for this work. Now we will why two derivative theories are good. Now we will explain the proof. We will just sketch the proof how we have got to this new rule. So as we said, that new rule will be proved from a scattering process. And that what is the scattering process? The scattering process is 1 and 2 are colliding, and then a classical scattering is happening, and then 3 or 4 are going to infinity, right? So this is usually called a lab frame, where the scattering region is static, or it is near origin always, right? So, and then in center of mass, you can immediately write a center of mass frame, right, where 1 and 2 are coming in opposite side, and then 3 and 4 are scattered, right? And in this process, you can define every quantity. If I have given you this E value and the theta value, right? For this scattering process, you can define a scattering amplitude, and that scattering amplitude can be written as an 1 plus I times t. This 1 represents the no scattering incident. Like, it can happen that 1 goes to 3 and 2 goes to 4 without any interaction. That is represented by this 1, and if anything happens between them, then it will be reflected in this t, and that t depends on two variables, s and t. These are redefinition of this E and theta. Okay, these are nothing but redefinition of this E and theta. And how they are related? E is equivalent to root over s, and theta is almost sine inverse minus t by s. So these are the relations. So this is basically dependent on energy of the incoming particles and the scattering angle. Okay, and these E, S and T are the variable I have talked about in the first slide, that large S and fixed T. So these S should be taken to infinity or large values, fixing this T to order 1 value. Okay. Now, all I said is that we want a classical scattering process, but we need to do some calculation, but we will do some calculation using field theory notation. Okay. For that, we will easily motivate you to this notation. And what it says that consider a state, two particle state at minus infinity, like time is equal to minus infinity, right? And then it's a two particle state, then it comes and then it scatter and then goes back to again two particle state, right? So it's a two particle state to two particle state transition, right? So how you can create a two particle state? You can create a two particle state by acting two phi's on this ground state, and then again you can create a two particle state in acting phi 3 and phi 4 acting on this ground state, and you call them the psi f and psi I. Psi I is the initial state, psi f is the final state. So the amplitude or the probability for going from psi I to psi f can be measured by this inner product, that is psi I and psi f, right? And then you can use this definition of the psi I and psi f. You can easily see this is an expectation value of this 4 phi's on this ground state, right? So these kind of things are usually called 4-point function. As we saw that 2 phi sandwiched by ground state is called 2-point function. Okay. Now the scattering amplitude, what we defined just previous slide, TST is mod of this amplitude square. Okay, you have to take the modulus and then you have to take square. So all this will be required because we are essentially, we have related the whole classical scattering process to a 4-point function in the bulk. Okay, oh, sorry, in the flat space region, right? Now, till now we have considered a flat space scattering process, right? Now you want to consider that scattering process in an ADS space. I will explain what is ADS. It is not too different from flat space. It has this metric. If you have read about metric, then you can see that this R parameter represents it is like a cylinder, okay? And it is like a cylindrical space, and the cylinder's radius is determined by this R parameter. And if you take that R to infinity, then you are effectively in a flat space. Okay, that's how you can see this ADS space. And I have just written down this metric to explain that this, if you take R to infinity, this one survives. If you take this capital R to infinity, then this one survives. And then this is basically a flat space metric. If you have written down any flat space metric in polar coordinate, this is just a polar coordinate flat space metric. Okay, so we will not need this metric anywhere, but we just wanted to motivate that the R tends to, capital R tends to, the radius of this ADS tends to infinity, gives us the flat space. Okay, and here I also want to mention that this ADS has two parts. You can differentiate two parts. That is the inside of this ADS and the boundary part. It has a finite boundary. It has reachable finite boundary. Okay, and the inside part has a name that is called bulk. I will use this name in few moments. Now, since we are in the ADS, we are considering the scattering in the ADS, we can use a well-known duality, and that says that gravity theory in this inside region or in this bulk region is equivalent to a thermal CFT in the boundary. Now, these are maybe complicated words, but this is nothing but a quantum mechanical system in the boundary. Okay, and it's a well-defined duality that any classical gravity theory is a dual to a quantum mechanical system in the boundary. Okay, so if you have any quantity in this boundary, you have an image of that process in the bulk. So you can find it always, and this goes as a name, that ADS safety duality, and this is a dictionary. Any quantity in this space has an image in this space. You can define another quantity which is exactly equal to that quantity. Okay, so you have understood that we will use some property of this boundary to constrain this, to get some bound on this bulk process, right? Because we are interested in this process. Now, what we know about the boundary theory? In boundary theory, we know something called a bound on chaos. Okay, I will explain what this is. So, what this says that at boundary, it's a thermal quantum mechanical system, right? And it shows a chaotic behavior. What do I mean by chaotic behavior? It just means that if you calculate the same 4-point function's image in the boundary, it goes as exponential of lambda L t, and t is the boundary time. Okay, so then this lambda L can be interpreted as Lyapunov exponent, right? And then there is a paper called A Bound on Chaos by Maldusana in 15. It says that this lambda L can't be arbitrarily large. Okay, it has an upper bound, and this is the upper bound. Okay, for any thermal system, and thermal system definitely will have some temperature, and you can associate Kb, and you have H bar because it's a quantum mechanical system, right? And then you can recover the classical result, because at classical level H cut is 0, tends to 0, right? And then this bound becomes like unbounded. You know, H cut goes to 0 means this number becomes infinity, and then lambda L can have any value they want, and classically that's what happens. We will use crucially this bound, okay, in the bulk. This is a boundary fact. Now, using, as I said, there is a dictionary to go from bulk to the boundary, and using the dictionary, one can associate this one can say that the S parameter, the S we have defined in the scattering process, right? That is exactly equal to e to the power twice by kBt by h bar times this time, right? So this time and S are the variable related, and this time is in the boundary, this S is in the bulk. Okay, so if you use this identity, then you can immediately show that in the bulk the same 4-point function grows as s to the power p, right? And now this bound, this Lyapunov exponent bound, imposes some bound on this p number, and the bound is p is much less than equal to 1. Okay, now you will use this bound in the bulk, because we are interested inside that cylinder. Then the scattering amplitude, as we said, that TST is mod of this amplitude square, which goes as this 4-point function mod square, because amplitude is 4-point function as we motivated, and then that goes as s to the power 2p, right? Since p is less than equal to 1, it can't grow faster than s. This TST can't grow faster than s square. This less than equal to is not in concrete sense. It says that TST can't grow faster than s square, and this is the rule. And hence we have proved the bound on this scattering amplitude. So now I will explain this whole proof as a summary in the summary slide. Now what we say, since it's maybe a long process, but we will summarize this this process. That we were interested, maybe you can't read some things, but it's okay, you just remember the images. Okay, so we were interested in this 4-point scattering amplitude, right? Two particles are coming in and two particles are going out. K1, K2 are the momentum, K1, K2, K3, K4, right? And this S is 1 plus IT. That's how we have defined our scattering amplitude. And then we have interpreted this process in a quantum mechanical sense, or using bracket notation, doing classical mechanics using bracket notation. And then the amplitude looks like this 4-point function, where TST, the same T, ST, grows related to this amplitude as mod A square, right? And then we want to calculate this 4-point function in this flat space region. Now we have only considered ADS, the same scattering amplitude in the ADS space, okay? And then using this ADS CFT duality, we have related the bulk to the boundary, and then we know some information about the boundary. That is, this 4-point function in the boundary grows as some exponential order, where this exponent has a bound, and that induces a bound in the bulk process. As we said, that every process in this boundary has an image in the bulk, and that image is this TST is less than equal to s square, okay? But you can ask, this is a proof in the ADS, right? So how can we say that in flat space also this bound is valid? But we can take a smooth capital R going to, the capital R is the radius of this space, right? So we can take a capital R going to infinity limit very smoothly, so that this relation holds everywhere. So it's valid in ADS and also in flat space also, but the proof goes through ADS space, okay? So still we don't know any argument in the flat space which will give this bound. We don't know any physical process or anything which can give this bound. Okay, this is the summary of the process. Now, what is the conclusion? Now the main part comes, because we have a new rule, and we also have a proof of that rule. But how to use this rule? To use this rule, first you have to you want to rule out some interaction in gravity or in other theories also, right? To do that, first you have to know how many interaction terms are there, right? So you have to categorize every interaction term in some basis vectors. We have categorized every interaction term. I mean, in this previous paper, so this 19 paper and also 20 paper, we have categorized all interaction terms possible, and then we have identified all those interaction terms which will contribute to this process. There can be many interactions which are not even contributing to this process. If it is not contributing to this process, then you can't say anything about those interaction terms. But if it is contributing, then you can definitely say something about that term. And we have explicitly categorized all those interaction terms, and the number of interaction is actually infinity. Then also, like, the full set is not covered, but the interaction term which contributes to this process is infinite number of interaction terms are there. And among all those terms, only classical, and we are also considering only classical interactions. So among all those terms, only Einstein action satisfies this bound that TST is less than equal to S square in gravity theory. Also, you can use this theory in use these arguments in spin 1 case, that is for photons, and also for spin 0 case, that is for scalars. And we also see some actions which are only 2 derivatives or maybe 3 derivatives. So there are very few finite number of interactions which satisfy this bound. Okay. Now, if one wish to, as we said, if one wish to keep infinite number of terms, then largest behavior may get cured. For example, as string theory, somehow it happens, we don't know it, but at least I don't know definitely. But yeah, so we know this example, and it is also valid for gravity theory, and also it is we have also constant spin 1 and massless Lagrangians, as we said. So this ends my talk, but yeah, so I can get some questions, or I can explain you few new things about this. I can motivate you about the chaos bound. That is how you can get a motivation for that bound on this lambda. So over to Ognivo, if you say what should I?
Yeah, I think you can have 10 more minutes if you want to
Okay,
continue.
great.
Okay.
No, maybe Ognivo, I can I say something? Sorry.
Yeah,
I
please.
think what I felt, this is my personal feeling, and it's totally up to the organizers and the speaker what they want to do. But I felt right from the beginning of Suman's talk that this talk, I think, works better if there are more questions in between, because it's done in that style. I felt that. So, but it's already
Yes,
up to
yes.
you on what you want to decide. Yeah.
Okay, no problem. Then we can have a few questions, I think.
Okay.
So there is already one question. Shayan Bhomik writes.
Yes, so
Okay.
we have a question in the chat box. So Shayan Bhomik asks, in ADS metric, there are 3 terms, dr, dt and d omega. How the term
Yes.
include with d omega work? I think he says that
Include
how
with
the word
d
d omega.
omega. Oh, do you mean what this d omega means?
Yes. I think.
I guess that is
Okay,
the thing.
so I can. Okay, so just one second. So d omega is nothing but a shear metric. So let me tell you. So for flat space, for 3-dimensional case, right? I am just ignoring the time coordinate, okay? And then you have this as a measure of any distance, right? Now you can do a coordinate transformation, that is z is equal to r cos theta, x is equal to r sin theta sin phi, and then y is equal to r sin theta cos phi, right? If you use this coordinate transformation here, you will see that this coordinate, the same thing looks like d theta square plus sine square theta d phi square. Okay, you just do this coordinate transformation and use this in this metric, you will see this part. Okay, so what I did, I just transformed the coordinate from Cartesian to polar, right? And this part is called d omega square. Okay, this is a d omega 2 square. So, and for higher dimensions, it is for 3-dimensional case. For higher dimension also, the same logic goes, and the answer is r square d omega d minus 2 square or d square, whatever you can write. So that's how this comes. And then if you just add a minus dt square here, you will get a minus dt square here, right? And that is the metric. And what we said that there are some factors here and here which goes to 1 in capital R, goes to 1 limit. So this is a flat space metric. If you Yes. Does that answer your question?
Okay, so I think he can write in chat. So let's move to the next question. We have a question from Ognivoda. So I'll request him to please unmute.
Hello, Sumanda. So
Yeah.
I just have two small, very simple questions which I missed at the beginning of the talk. So can you go to your first and second slides? I think the next one. So,
Yeah.
so what is small s and small t here? So what do they mean?
What do they mean? Yes, I knew that. Okay, so I should go to the 10th slide. Okay. What we want to consider is a scattering process. It's a simple 2 to 2 scattering. One first particle and second particle are coming, they're interacting, and then 3 and 4 are going back to infinity, right? So any scattering process, this is in lab frame. You can't identify the data, you need to specify the process. But you can see in center of mass frame, what are the independent data you have? How many data you need to specify a scattering process? That is this energy of this incoming particle and the scattering angle at which this scattering is happening, right? So these are the two data you need to specify any 2 to 2 scattering. And this S and T are related to this E and theta, which what you know through these relations. E is just root S and theta is sin inverse minus T by A. So T usually determines the angle, how it's scattering, and this root S is determining the energy.
Okay, and you have kept t fixed there. So is the reason why you kept t fixed for your derivation in the second slide?
Sorry.
So you kept t fixed, right? You kept t fixed there and just say that.
Yes. I kept t fixed. Yes. I kept t fixed.
Okay.
Sorry, can I just make a comment? I mean, Suman, would we be completely wrong if we assume that S is actually the action and T is time? Is that possible?
No, these are called Mandelstam variables. You know, these are some
Mandelstam variables.
Yes,
okay.
These are STU are the Mandelstam variables, and these are explicitly related to the scattering data. That to define a scattering, how many data you need? Okay.
So this has nothing to do with an action.
Nothing to do with anything related to capital A scattering S matrix or action or time t.
Okay. And just one small thing. I'll be done with it. So can you go to the next slide again? Yes. So you said that 1 by 1 minus S is of the order of 1 by S. So how do you say that?
Because we are considering large S of this expansion. Now you can ask another important question, that if S is large, then how can you sum this series to give this 1 minus S, right?
Right.
Now the answer to this question is it's a non-perturbative effect, right? So the answer is actually 1 by 1 minus S. You have explored the low energy region, and that's why you got this result in this form. So, you know, and the starting point is this, because you have non-perturbative effect. But you have expanded your result in other, like in low energy region. That's why you got this S squared terms. And then you can't question the main answer. And this is the main answer. Okay. That's how it is interpreted. Like, yeah.
Okay. Thank you.
Okay. So one question we are having from Ashif Akram. So I'll request him to please unmute.
Hello, Suman.
Yes.
Yeah, I'm Asif. We have met IIT Bombay. So my question is, here you are talking about the two derivative theories being good theories, right?
Yes.
And the way you are trying to motivate is, you are showing that some limit, there is some energy limit which is less than kind of S square, and that is equivalent to some second derivative theories, right?
Not exactly like that, but yeah, it's related to that. But we have seen three derivative theories also got, like, if you have S square behavior, it's not exactly related S square to two derivative theories, but usually two derivative theories gives S square, but there are some theories with three derivative but giving S square, so those theories are
Okay.
also allowed.
Okay, so the S square basically limits its up to the three derivatives. That's what you are saying.
The derivative counting is just for motivation. S square is more concrete than derivative counting. I mean, yeah. So using derivative counting, you can't say, we are not saying any rule involving derivative counting. We are just motivating the work from derivative counting. But the main result is S square. Okay. So if you have any interaction with 10 derivatives, if it gives S square, then you are okay.
Okay. So basically, but still that's a finite number of derivatives. That's the point.
Yes, that's the point. The point is you can't have infinite. Usually what happens, all these theories comes as a limit of lattice theories, right? You consider some discrete theory and then you take limits. Now, if you have infinite number of derivatives, to define a interaction of that infinite number of derivatives, you need the whole region to define a single term. Like these are not local interactions usually. So usually infinite number of derivatives are very dangerous. Yeah.
So for example, the theories which has ultraviolet divergence or infrared divergence, how will they look like in that case?
Divergences usually comes in quantum as a quantum effect. We are considering classical theories. So till now we have not seen any kind of divergences in the theory, because usually divergences comes from the loop diagrams, right? So we are not considering loop diagram. We are only considering tree-level diagrams which don't have any divergence at all. So those are very well-defined results. These are just simple poles. We are not even considering branch cards. Yeah.
Okay.
Yes. Thank you.
Okay, I'll come back later again.
Okay, so let's move to SS sir.
Yes. Hi, SS sir.
Hi, Suman. Nice talk. Well, my question is like, so you are trying to say why Einstein theory is good, saying that it has. Now, if you know that there are several theories that has been proposed to explain the dark matter in a different way. Modified theory of gravity. Can those be ruled out, or can those be, some of them should be satisfy this condition? Can you say something on it?
Exactly, that's what we are trying. We are in the very preliminary stages of this, because this chaos bound came in 2015. So it's very new study. We are making it concrete. We can't say anything before getting a bulk argument. This proof comes as a bypass through this ADS space, right? As I said, that we are using the ADS boundary and we are using this ADS CFT duality, and there are some questions about ADS CFT duality. So the next goal is to find out a physical principle in the flat space itself. Let's say it might be causality, that a process should be causal, okay? And then you are just checking whether which interaction is giving a causal process, and then you can check that just the next term to Einstein, that is the Gauss-Bonnet theory, is violating a causal process, and that is already established in, I think, 2012 paper. That they have considered a single scattering process. Yes. So they have considered a single scattering process in Gauss-Bonnet theory, and they showed that this term cannot be there because of causality. So we believe there is some argument like causality or unitarity will give this same S square thing.
Okay. Thanks.
So we are looking for that argument, because then we can use argument in DS space also. So, yes.
Okay.
Hello?
So Soumendra da.
Okay, I have actually few questions. So let me ask
Okay.
one first. So, Shumanda, so can you go to your pound slide? I mean, Malda Senator 2015.
Yes.
Yeah. So actually, when you calculate S in the ADS space, so basically Mandelstam variables are defined in flat space time, right? So when you
Yes.
define Mandelstam variable in ADS, so
Yes.
how do you take the non-trivial effect of some quantum
See,
filter in curve space time? Because SQ
I
are
understand.
I mean, you need to calculate S matrix, right? You have calculated the 4-point correlator. That is basically
Yes.
some sort of A dagger, and then you calculate. So you need to
Yes.
go to the quantum thing. So how do you write
No.
STU in ADS to calculate this 4-point correlator?
First, I want to tell you one thing, that this S, in which space S we are considering, is a totally classical theory. Okay, the left hand side, the bulk, the inside part, the where we are considering the scattering is happening, there the theory is classical. So you don't have any quantum effect in that side, right?
Okay.
Do you agree with this statement?
Yeah.
This is the first important statement. Okay, so there is no quantum effect in this S side. Okay,
I mean, then
now
S is
look,
just. I mean, then S is
flat
just center
space.
of mass energy, right? The
I
interpretation
understand.
of S is just center of mass energy.
Yes. So
Okay.
your question is basically, this S is always defined in flat space. How you are defining S in the bound in ADS, right?
Yeah.
So this S is not exactly the same S, but whatever this quantity in ADS is, its limit in R tends to infinity is this small s. Okay, so that's how this identification goes.
I mean, but then the same question remains, right? I mean, when you take the ADS CFT, then in the ADS limit, in the ADS space, what does this S, T, U, and all other variable mean? I mean, what do they signify?
Okay, so let me tell you that in ADS, instead of this ST, basically in STU, there are only two independent variables, right? Because of
Yeah.
the relation, S plus U is 0 or something else.
Okay.
But similarly, in CFT, you have two cross ratios, U and V, right?
Yeah.
So this U and V has a particular limit, has a particular limiting value in R tends to infinity. These U and V are very well defined in ADS. Do you agree? The cross ratios are always well defined in ADS. Okay.
Okay.
Then you can take R tends to infinity limit of these variables, and then you get S and T. Do you understand?
Okay.
Okay. Or I can tell you in more detail. Let me tell you because it's important. Okay. So let me tell you. Usually, any CFT correlation function, okay, are functions of U and V, right? Now you can do one kind of transform, that is, you have done Fourier transform, you have done various transforms. There is something called Mellin transform. Okay,
That I don't know, but okay. Yeah.
okay, fine. Though you don't need to know, it's fine. I'm just telling you what is the transform is. It is very simple. It's U and V. Let's say these are the CFT correlation function in ADS space with these cross ratios, right? And then you are defining U to the power S, V to the power T. Okay, and then you are integrating over du dv, right? Now if you do this integral, then you get a function of S and T, right?
Yeah.
And these are usually called, let's say, MST. We just called it. Okay, then people have seen that at R tends to infinity limit, this MST goes to this TST. That's how these S and T are related to ADS space. Do you understand?
Yeah. Okay.
Yes.
So,
Okay.
can I ask another one, Ognivo?
Oh yes, please.
Or
Yes, I think
okay.
you can go on.
Okay, so the next thing is when you say that you want to derive the Einstein-Hilbert action. So in the Einstein-Hilbert action, you want to not derive, but you want to check that whether Einstein-Hilbert action or any other action, obeys this bound or not.
Yes.
So basically, do you have the Hawking-Gibson boundary term, or don't you have the Hawking-Gibson boundary term?
You don't have, because that don't affect the bulk scattering. Hawking, you are saying that it's a boundary term, right?
Yeah.
So boundary term usually don't affect any bulk process. Okay.
Yeah,
It's
but
just classical. Yeah. So
but this term is important when you calculate the things like black holes or something like that. These are boundary terms, I agree.
okay,
but,
okay. So in that case, I can say that the boundary is the CFT. So your space is effectively infinitely spreaded, right?
Yeah.
So there, the boundary terms are usually important when you have a boundary at a finite reach, and for this case, this actually don't affect anything. Right? And because this is an ADS space and the boundary is totally decoupled from the bulk. So any process happening in the bulk can't have any effect from the boundary, because all these are local interactions. The two particles are coming and going back. You are not considering boundary terms are usually very non-local term, because it connects a huge long distance interactions, right?
Yeah.
So for any classical local interaction scattering amplitude, the boundary term can't contribute to that scattering process.
Okay.
Yes.
So actually, I have another questions also, but I will ask later. I think this will lead to a discussion, I think. So I will ask in the discussion section.
Okay, so ma'am, I think you can go on with your question.
Okay, Suman, nice piece of work. Now, my question is extremely basic. So, can you go to some of your previous slides? যেখানেতে তুমি essentially you are talking about the truncate. Yes. So, next slide. Truncated.
Yes.
Truncated theory, you are calling it. Yes. Yes. Yes.
Oh, truncated.
You have this expansion. Yeah.
Oh, I have this expansion. Okay.
Yes. Yes. And here, what is this?
This
is your Mendelssohn variable or what?
Yes. Yes. This S is Mendelssohn variable.
Now, if you go to the slide where you mentioned the Einstein-Hilbert action.
I have mentioned the Einstein-Hilbert action.
I think you wrote something that I did not understand. That's why. This is all your proof. Now you are testing, testing with the Einstein-Hilbert action. Yeah.
Oh, testing with the Einstein. That's in the conclusion page. Yes.
Yes. So you are saying only Einstein-Hilbert action passed the test as the only good truncated classical gravity theory. Now, is this truncated the same as the other truncated that you used previously?
Exactly. Said.
So can you explain that from that equation, the 1 plus the man from that business, can you explain why is your Einstein-Hilbert a truncated good truncated classical theory of gravity? Just, you don't have to be very detailed, just simply explain. And I think so. Am I correct in assuming that it is definitely a good theory but not the good theory? This is consistent but not the only consistent one. Am I right in assuming that?
Definitely not the only consistent, because there are many interactions which are higher order in the end, but they also don't contribute to this process. The statement is, if it don't contribute to this scattering process, we can't judge, we can't say anything about those interactions, right? So
তাহলে
it's
তুমি
not,
ওইটা একটু এক্সপ্লেইন করো যে আইনস্টাইন হিলবার্ট অ্যাকশন যদি আমি দেখি সেটাকে তুমি যে একটা গুড ট্রাঙ্কেটেড ক্লাসিক্যাল থিওরি বলছো from that context সেটা কেন, why is that?
So okay, so you can start with any number of interaction terms, right, in gravity. Let's say how many two derivative theory, how many two derivative action you have in gravity. There is only one, that is Einstein action. Okay, there is no other two derivative theory you can write down except Einstein action. Okay, so you have the next term is fourth derivative. Okay, the another one is sixth derivative.
Okay.
And that's how you can introduce your interaction terms, right?
Okay.
So all modified gravity theories are more than two derivatives. Okay, now you can categorize those interaction terms. Now you just declare that I will only work with up to 6 derivatives, right? And there is no other term in my theory. Okay, if you declare this, then this theory will violate this s square bound. Okay.
Okay, so am I then Suman, then is it okay to say that because Einstein Hilbert doesn't have fourth order term, right? Interaction.
No.
Right?
No, fourth derivative term is not there. There are only two derivatives.
Only two derivative term in Einstein Hilbert action.
Yes.
So আমি দুটোর মধ্যে তফাৎ করতে চাইছি যে ধরা যাক আমি একখানা অ্যাকশন লিখছি which has these two derivative terms only. Will that satisfy your criteria, or is it just that the Einstein-Hilbert action specifically satisfies?
Oh, you are asking.
That's the question. Is it the only second derivative theory, or can I construct any second derivative theory, any theory which is the second derivative theory, and it will be still consistent?
As far as gravity is concerned, as far as you are considering G mu nu as a metric, and you are imposing Lorentz invariance, then you can't construct any other scalar out of this Lorentz invariant G mu nu with two derivative except Einstein action. That's for sure.
So that means if you want to modify your gravity from Einstein action, from GR, from Einstein's theory, then you have to modify the action and you have to go to higher derivatives. Am I right?
You have to go to higher derivative, or you can include other fields, like let's say phi into r is another interaction term possible, right? So you can multiply other fields to create interactions, but using gravity is the only two derivative action.
Einstein Hilbert is the only two derivative action possible.
Yes.
Okay, thank you.
Yes.
Okay, so Shumanda, we have two more questions, but I think I'll request you to please go on with your chaos bound for maybe 2-3 minutes, and then we will come back to the questions.
Okay, great. So I just wanted to motivate this process. This is not definitely a proof, and the proof is very complicated, but I just want to say that using very simple facts about uncertainty principle in quantum mechanics gives you almost this bound. Okay, so let's start. It's very simple. It says that since you are in thermal quantum mechanical system of temperature, let's say T, then you can define that there is an uncertainty of energy of cavity. All these are rough statements, okay, because this is not a proof. And if your system, if you have a system and then it has some quantity, this delta y is representative of that 4-point function. So at time t, if it grows as delta y 0 at e to the power lambda lt, then you can define a time scale with this process. You can immediately define a time scale with this process, that is delta t, which goes as 1 by lambda l, because this delta tau is lambda l. And then you can easily use uncertainty principle, that is delta e delta t is greater than or equal to h bar by 2, which you can just where you can just use this delta e and delta t value kbt by lambda l, which is greater than or equal to h bar by 2, and it gives lambda l is less than or equal to 2 kbt by h bar, and the answer is there is a pi here, okay, and it's just off by a pi. So that's how you can just see it, but the proof is very, it is detailed, and it uses complex analysis very extensively. So that's it. Thank you. I'm sorry, short, but
okay. So
if you have any question on this slide, you can ask. one
Okay,
can
so
ask. Yeah.
I think Soumendra Da, I'll go with Soumendra Da first.
Yes. Yes. Yes.
আচ্ছা, আমি বাংলায় বলছি একদম সহজভাবে। সেটা হচ্ছে যে
হ্যাঁ।
হ্যাঁ, যেটা মানে তুমি যখন প্রুফটা করার চেষ্টা করছো যে আইনস্টাইন হিলবার্ট অ্যাকশন এই বাউন্ডটাকে পালন করে বা ওবে
হ্যাঁ।
করে, সেখানটায় তুমি মানে কিভাবে এই এস থেকে ওই প্রুফটা মানে রিলেট করছো কিভাবে? মানে তুমি কি ফিয়ার্স পাউলি অ্যাকশন থেকে শুরু করে হায়ার অর্ডার ইন্টারাকশন টার্মগুলো যোগ করে সেই এস গুলো সাম করছো? মানে তোমার এসটা এখানে কি মিন করছে?
সরি আরেকবার আমি শুনবো, ঠিক আছে কোশ্চেনটা?
মানে আমি বলছি যে তুমি যে যখন বলছো যে আইনস্টাইন হিলবার্ট অ্যাকশন এই তোমাদের মানে এই গুড থিওরির যে মানে এই মানে মানে আমাদের যে টি যে লেস দ্যান এ স্কোয়ার হতে হবে, তুমি যেটা দেখাচ্ছ সেইটা এই বাউন্ডটা যে মানে ওবে করছে, এখানে তোমার এসটা আর কি মানে তুমি এটার সঙ্গে আইনস্টাইন হিলবার্ট অ্যাকশনকে রিলেট করছোটা কিভাবে? মানে আমি রিলেশনটা
দ্যাটস এ গুড কোশ্চেন। সো ঠিক আছে, তাহলে আমার এইখানে যাওয়া উচিত। সো দিস ইজ দ্য ডায়াগ্রাম। ওকে, it's a very general concept that if you interact two particle with any interaction term, okay, you can calculate some scattering amplitude corresponding to that interaction term, right?
Okay.
And Einstein Hilbert action is a interaction term. It's a very non-local interaction term. If you see it very, I mean, explicitly, you will see it's a very non-local interaction, but only have two derivatives. It's a very beautiful theory. So,
মানে আমি এখানটা একটু ইন্টারাপ্ট করছি, সেটা হচ্ছে যে ইন্টারাকশন টার্ম মানে ইন্টারাকশন টার্মে তার একটা ফ্রিফিল টার্ম আছে, মানে সেটা তো তুমি বললে মানে সেখানে ফিয়ার্স পাউলি থেকে শুরু করে বাকি রেস্ট অফ দ্য ইন্টারাকশন টার্মসটাকে তুমি বলতে চাইছো, মানে আইনস্টাইন হিলবার্ট অ্যাকশন ইন্টারাকশন টার্ম মানেটা কি?
Okay. So yeah. So interaction টার্মটা কি করে রিয়েলাইজ করা যায়? Obviously Einstein action থেকে কি করে, so how can you see that this is an interaction term? So for that you can do one thing. So just let me go to this. So R, okay, and the equation of motion for Einstein equation is like this, is equal to 0, you can say. There is no matter. Okay, so this is the equation, right? And this is a function of g mu, right? This is the metric. Now you can see that now you just do one thing, that is g mu nu is flat space. This is the flat space metric, that is there is nothing, plus an h mu nu. Okay, and this is very small, so mod of h is much less than 1. Okay, if you consider this, then you can calculate this r mu nu, okay, as a perturbative series. Then you will see this equation looks like roughly this term, box square, this D'Alembert h mu nu plus some higher order terms in h mu nu, you know, h mu nu, h alpha nu. Okay, so order h square term plus order h cube term. So that's all, right? And this will reduce to this equation. This is the free field part. This is the free field part, and these are the interaction terms. So whatever effect we are getting from r mu nu is the effect of all these interaction terms. So we are considering r mu nu as a single interaction term which have all these effects. Okay, that's how it is interacting. R mu nu itself is a very complicated interacting term. You can, yeah.
আচ্ছা, আমার এখানটাতে একটা প্রশ্ন আছে, সেটা হচ্ছে তুমি যখন এটা বলছো তখন তুমি মানে বক্স মেইচ নিউ মানে এটা তো সিম্পল একটা ফ্ল্যাট স্পেস টাইম স্পিন টু থিওরি থেকে শুরু করে তাকে আমি তারপরে ইন্টারাকশন টার্মগুলো কাপল করে আইনস্টাইন হিলবার্ট অ্যাকশন তৈরি হয়েছে বটম আপ অ্যাপ্রোচে। এবার হচ্ছে যে হ্যাঁ, এবার এখানটায় মানে আমার মানে একটা বেসিক কোয়েশ্চেন আছে, সেটা হচ্ছে যে তখন আমরা পাউলি ফিয়ার্স অ্যাকশন লিখছি বা ফ্ল্যাট স্পেস টাইম স্পিন টু থিওরি লিখছি, তখন তার একটা মানে নন ট্রিভিয়াল এনার্জি মোমেন্টাম টেন্সর আছে, এবং যখন আমি সাম আপ করে গোটা আইনস্টাইন হিলবার্ট অ্যাকশন লিখছি তার এনার্জি মোমেন্টাম টেন্সর হচ্ছে 0, কারণ তার কোনো এনার্জি মোমেন্টাম টেন্স থাকে না, মানে শুধু ফিল্ডের বলছি, ফ্রি ফিল্ড। তাহলে মানে মানে তুমি যখন এরকম এক গাদা ইন্টারাকশন টার্ম যোগ করছো তখন তুমি একটা মানে লম্বা সিরিজ যোগ করে কি করে 0 পাচ্ছ? You have some finite term in the lowest order, but when you sum up the series, then you are getting 0. So how do you get that?
How do you get that? That's I don't have any answer to this question very seriously, but what I can say now, if you ask this question, I will remember how Einstein got his equation, right? What are the assumptions he made so that this equation is the only possibility in two derivatives, right? So that comes as the demand that this r mu nu minus half r g mu nu should be divergence free,
Okay.
because your energy momentum tensor is divergence free,
Okay.
right? And the second idea is the equation should be general, so covariant, like the equation should not change with change of the metric, the coordinate transformation, right? But here you see, you know, how should I say it? You are asking that if you considered only these two terms, right? Why this is not a gravity theory?
No, সেটা আমি জিজ্ঞেস করছি না। আমি বলছি যে সিম্পল বক্স এইচ মিউ নু ইকুয়াল টু 0 এর অ্যাকশন লিখে যদি আমি সিম্পল একটা নোয়েদার এনার্জি মোমেন্টাম টেন্সর বের করি, সেটা নন জিরো টেন্সর। এবং তারপরে আমি যদি এই সমস্ত টার্মগুলো ইন্টারঅ্যাকশন টার্ম একটা করে নিচ্ছি এবং একটা করে টার্ম যোগ করে যখন ফুল সিরিজটা পাচ্ছি, তখন আমি যদি দাবি করি এটা আইনস্টাইন হিলবার্ট অ্যাকশন হতে হবে, তাহলে ইট মাস্ট বি 0, কারণ আইনস্টাইন হিলবার্ট অ্যাকশনে এনার্জি মোমেন্টাম টেন্সর মিউ নু 0। তো তুমি লিখেছো আর মিউ নু ইকুয়াল টু 0। এবার ঘটনাটা হচ্ছে যে মানে হাউ ডু গেট সাম, মানে তুমি কি করে একটা জিরো পাচ্ছ, মানে কিছু যোগ করে এত বড় একটা সিরিজ জিরো পাচ্ছ, এটা তো একটা আনক্যানি ব্যাপার।
Definitely, but I think it goes in the other way, that you got r mu nu and then you expanded to see it 0. But definitely I don't know why this, I mean, I don't know which physical principle says that it should be 0, but yeah, but general covariance and this divergence should be 0 leads you to this, only this r mu nu is equal to 0. There is no other option, right? I mean
মানে আমার
why this sum up to 0, I don't have any argument to, like, I mean, why this sums up to 0?
Can I just make a comment? Sorry, if you don't mind, can I make a comment? আচ্ছা সুমন, তোমার যে তুমি যখন h mu nu টা লিখেছো, g mu nu হচ্ছে এটা mu nu প্লাস h mu nu, তুমি একটা স্মল একটা টার্ম লিখেছো, রাইট? h mu nu is general, right? There is nothing specific about h mu nu. It's a
no, it can depend on it can depend on x.
Yeah, that's right. It can depend on x. That's right. But there is nothing. There is no constraint on h mu nu, except that it is very very small. সেই ক্ষেত্রে I think Somendro's question, if I understand correctly, that if I have a very general h mu nu and an infinite series with many orders of this business with this box D'Alembert, how is it ensured that this series is going to be 0? Because his h mu nu is general. Am I right, Somendro? Is that the concern?
ঠিক একদম।
আর আমি তো কোনো কনস্ট্রেন্ট বসাচ্ছি না h mu nu এর উপর।
একদম আমি বুঝেছি কোশ্চেনটা। সো এই কোশ্চেনটার অ্যানসার আসলে সব, every fact about this infinite series goes to the same answer, that it's a non-perturbative effect, and you know it's very hard to control the infinite order terms, and in many cases it sums up to 0. It sums up, I mean, positive numbers summing up to minus 112, and there are many things of this kind happens. And
Suman, it's a vacuum solution. Your r mu nu is 0. That directly gives you this infinite series as equal to 0, right?
Yes.
Yeah, but then actually
they're asking the opposite one.
Yeah, I think it's the opposite question.
In opposite sense, why this sums up to 0?
Yeah, I guess it might be asymptotically it's very close to 0, and then is that possible because it's such small? Because otherwise I don't see any reason for that.
Exactly, this exactly goes as this argument, you know, where I have said that this series comes up to this 1 by s. How can you say that at large s you see this series diverges, this whole series, right? This whole series diverges if you take just naively s tends to infinity, right? But you see that same thing giving 1 by s behavior. Now it's very, now the argument can be that the actual answer is 1 by 1 minus s. You just expanded it in low energy limit. So the answer to that question, what you asked, is that it should be that, you know, you have R mu is equal to 0 as your answer. Now you are expanding your answer in h mu small case, and you want that sum up to, and it should be convergent at all. I mean, it should be convergent. It should satisfy everything. But that will not. Those are usually.
মানে আমার এখানে যেটা বলার বক্তব্য, মানে যখন তুমি বটম আপ অ্যাপ্রোচ নিচ্ছ, তখন বেসিক্যালি তুমি জিআর বা জিওমরফিজম ইনভ্যারিয়েন্স আছে তোমার থিওরিতে, বাট সহজ ভাষায় জেনারেল কোঅর্ডিনেট ইনভ্যারিয়েন্স আছে তোমার থিওরিতে, সেটা তুমি ধরছো। তুমি স্টার্টিং ফ্রম আ লোরেঞ্জ ইনভ্যারিয়েন্স থিওরি, মানে ধরা যাক আইনস্টাইন নামে কেউ ছিল না, তাহলে আমি এবার শুরু করছি হচ্ছে একটা ফ্ল্যাট স্পেস টাইম থিওরি থেকে, যেটা পাউলি পিয়ার্স বলে দিয়েছে, যেটা একটা ইউনিক থিওরি। সেখানটা থেকে আমি সাম আপ করে 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 গোটা থিওরিটা তৈরি করবো, ইন্টারাকশন গুলো সাম আপ করে। সেটা হচ্ছে ভাই এনার্জি মোমেন্টাম ট্রান্সলেশন, আমাদের ট্রান্সলেশন ইনভ্যারিয়েন্স থেকে আমি এনার্জি মোমেন্টাম প্রিন্সিপাল কাপল করে গোটা থিওরিটা। এবার এই থিওরিটা যখন করছি, তখন কিন্তু আমি কোনো ডিফিওমরফিজমকে প্রুফ করছি, তখন কিন্তু আই ক্যান নট মানে বলতে পারি না যে হ্যাঁ ডিফিওমরফিজম ইনভ্যারিয়েন্সে বা আর মিউ ইকুয়াল টু 0 আইনস্টাইন বলে দিয়েছে বলে এটা হয়, কারণ আমি তখন অ্যাকচুয়ালি উই ট্রাই টু প্রুভ দ্য আইনস্টাইন। So basically this is the other way around.
You know, that's the point. You know, you can't just derive Einstein equation just one. I think definitely I don't know the answer in bottom up approach, but I can say one thing: you can't just derive Einstein equation without assuming diffeomorphism invariance, right? I mean, there can be many interaction term possible with G mu which are not diffeomorphism invariant, and there are interaction term possible that is Einstein action. So without that assumption, the theory should be diffeomorphism invariant. You can't lead to
Suman, we will continue in the interaction session. I think Pratik has a question. Pratik Nandi, he has a question from a long time.
Great.
Yeah.
Hi, Pratik.
Hey, Suman.
Hi.
Nice talk.
Great.
So my question is, I was just wondering if you are doing a scattering experiments in the bulk, right? So
yes,
doing the scattering experiments in the bulk and having some bound on this scattering matrix, can you have some construction of bulk operator in terms of the boundary operators? You know, this reconstruction program and everything. So
no, I didn't understood. Please just
so you are doing some scattering experiment in the bulk, and by having put some bound on this scattering matrix, can you say some information about how these local bulk operators are smeared in terms of this boundary operator?
So it's the boundary, right?
Yes, in the boundary.
Great. So yeah, this is a good question, and yeah, obviously this is a good question. So the answer is, you know, in ADS, if you have this ADS space, okay, and then if you have just a single insertion point, and then you are just exploring its propagation, right, in the bulk. So that's how it will propagate. It will be in a huge extended region. It will meet at a huge extended region, right? And then you can't take r tends to infinity limit to have a scattering in the flat space, right? Because in the end we want to take r tends to infinity, and this region also explodes to infinite region. Then in that case you have to smear this operators here to control this growth, right? And the growth functions, if you definitely know the variables are tau and theta, the boundary variables. Time tau and theta is this circular angle. This all this sphere is here. Okay. So then the L functions are like tau by delta tau and theta by delta theta. Okay. And this delta tau and delta theta satisfies some like growth properties, and delta theta is much less than 1 by omega. And that's how you can like create a wave packet so that it only meets at origin. You know, this you are just making it decoherence in this whole process just to concentrate on the origin. Okay, so that's how it is smeared, and yeah, we are using some smearing.
Okay.
This is the whole smearing function.
I see.
Yeah, thank you. So, Ognibho, I guess we have to move on to the interaction session because I'll have to leave at 8:30.
Yeah, sure,
So,
sure.
and then
I was also
can
thinking
have
about
more
that.
questions. Yes.
So, Shomendra da, if you have any more question, I'll request you to please get in touch with Shumanda personally. Okay,
please.
so we have an interaction session coming up next. But before that, I want to just request Shumanda to stop sharing. And
yes. And thank you everyone for attending this talk.
Yes, thank you so much for the talk.
Thank
I
you,
hope you
Shumanda.
enjoyed. Yeah.
So I'll just take a moment to announce the next talk. So is it visible?
Yes.
So our next talk is by Atreya Mojumdar, 9th September.
Wonderful.
We'll look forward to your participation. So now I'll hand over to SC ma'am to conduct the interaction session.
Okay. Thank you so much, Ognibho. Suman, এবারে আমাদের যে অ্যাকচুয়ালি ওই আমার একটু আজকে টাইমের তাড়া আছে, তার একটা কারণ হচ্ছে এসএস স্যার আমার বাড়িতে আসবে, ওই জন্য এক্ষুনি এসে যাবেন। তা সেই জন্য এমন কিছু নয়, কিন্তু হ্যাঁ উনি এই যে এক সেকেন্ড একটু, এবার ইন্টারাকশন সেশন যেটা হয় এটা হচ্ছে মোস্টলি আন্ডার গ্রাজুয়েট এবং মাস্টার স্টুডেন্টদের জন্য। আমাদের